Welcome to our Computational Fabrication Seminar 2022. I'm Rulin, the host today. We have two speakers for today's section. Welcome to our Computational Fabrication Seminar 2022. I'm Rulin, the host today. We have two speakers for today's section. Welcome to our Computational Fabrication Seminar 2022. I'm Rulin, the host today. We have two speakers for today's section. Welcome to our Computational Fabrication Seminar 2022. I'm Rulin, the host today. We have two speakers for today's section. Welcome to our Computational Fabrication Seminar 2022. I'm Rulin, the host today. We have two speakers for today's section. Welcome to our Computational Fabrication Seminar 2022. I'm Rulin. We have two speakers. Let's start by introducing one of our two speakers. Let's start by introducing one of our two speakers. The first speaker is coming from Singapore University of Technology Design, Professor Peng Song. He's now an assistant professor in SUTD. He received his PhD in computer science from Nanyang Technological University in August 2013. Prior to joining SUTD, he was a research scientist in EPFL, an associate researcher in University of Science and Technology of China, and a research fellow in Nanyang Technological University. Even earlier, he received his master's degree and bachelor degree in Harbin Institute of Technology, China. His research interests lie in computer graphics with a particular focus on the modeling, processing, design, and fabrication of digital 3D geometry. Let's welcome Professor Peng Song to present the motivational part of this talk.
Okay. Thank you, Ronnie, for the introduction. Computational design is an emerging research area in computer graphics. So in this motivational talk, I will focus on computational design of mechanisms. Mechanisms are everywhere in our daily life. A mechanism is an essential component of mechanical toys, clocks, vehicles, machines, and robots. In a mechanical toy, the 3D can follow mechanism drives the character's interesting motion. In a clock, the gear train mechanism transfers a single driving motion from the power source to the periodic motion of the second, minute, and hour hands, respectively. A planar gear linkage mechanism can be used to draw a 2D picture precisely and repetitively, while a special linkage can be used to performing pick and place tasks in factories. A mechanism is an assemblage of parts arranged and connected to transfer motion and forces from a power source to an output. Look at this example. The power source is applied on the gray part such that it can translate horizontally. The output is a motion of the gripper for grasping some objects. In a mechanism, each part is usually modeled as a rigid body. In this example, we have 6 mechanical parts. These mechanical parts are connected by joints to restrict their relative motion. In this example, how many joints do we have? The answer is 7, as highlighted here. Each joint is used to connect a pair of parts. Hence, a mechanical joint is also called a kinematic pair. A kinematic pair is a connection between two rigid bodies that imposes constraints on their relative moment. Here are three kinematic pairs. The left one is a spherical joint where the contact region between the two parts is always a surface. We call this surface contact. The middle one is a pair of super gears, and they always have a line contact. In contrast, a pair of spiral gears always have a point contact. A kinematic pair with a surface contact is called a lower pair, while a kinematic pair with a line or point contact is a higher pair. Due to the surface contact, lower pairs are more wear-resistant, yet also have a larger friction. In contrast, higher pairs have a smaller friction and can transfer motion more flexibly. Denote the poses of the two parts in a kinematic pair as M1 and M2 respectively. These two poses are a function of time since they keep changing when transferring motion. The motion constraint enforced by the kinematic pair can be written as F_m1t m2t equal to 0. In this equation, F is the motion transfer function determined by the joint geometry. We can combine multiple kinematic pairs to form a kinematic chain for transferring more complex motions. A kinematic chain is the combination of kinematic pairs joined in such a way that the relative motion between them is completely constrained. Here we show a kinematic chain with 3 parts and 2 joints. We can write the motion constraints for each joint, FA m1t m2t equal to 0, and B m2 m3t equal to 0. Let's assume m1t is the input driving motion and m3t is the output motion. Then the motion transfer function of this kinematic chain can be written as m3t equal to F m1t. This motion transfer function can be obtained by solving a system of the joint motion constraint equations. A mechanism may have multiple kinematic chains. We can use the same method to compute a motion transfer function for each kinematic chain in the mechanism. Now we know how to compute the motion of a mechanism with knowing geometry. In this example, the motion of the green ink is the driving motion, which is a simple rotational motion. Given the mechanism geometry with 4 joints, we want to compute the output trajectory of the end effector, which is shown in red. We call this problem kinematic modeling or simulation. A more challenging problem is mechanism design. Given the output motion, how can we design a mechanism that transfers the motor's driving motion to the output motion? In this example, given the output motion trajectory, we determine the topology and geometry of the mechanism as a 4-bar linkage shown here. People design mechanisms for 3 different goals. The first goal is to force a point on an end effector to move along a prescribed trajectory. This goal is called path generation. In path generation, we are only interested in the motion of an end effector point, such as connecting points of a toy character's head, tail, and feet, foot tips of a working robot, and the pen and point of a drawing machine. The second goal is to guide a rigid body through a series of specified positions and orientations. This goal is called motion generation or rigid body guidance. We can design a motion generation mechanism to drive an automata such that its motion can resemble motion capture data from human beings. Also, we can design a motion generation mechanism to drive an elephant toy such that its nose can mimic the movement of a real elephant. The last design goal is to cause an output link to move according to a specific function of the input motion. This goal is called function generation. Currently, there are very few computational methods for designing function generation mechanisms. Traditionally, mechanism design is a challenging task restricted to professionals, since it requires extensive knowledge in geometry modeling, mechanical engineering, and rapid prototyping. Here is a diagram that shows the traditional design process. One first draws some sketches about the mechanism, and then do some research and plan to choose mechanical parts and their connection. Next, he or she does the fast prototyping to evaluate its performance. In case the performance is undesirable, he or she may need to investigate the reason. If it is because of fabrication, then he or she needs to redo some prototyping. If it is because of the design, then some adjustment on the mechanism design may be necessary. To obtain a desirable mechanism, many iterations among design, prototyping, and evaluation are needed, which can be very costly. With the advances of digital fabrication, especially 3D printing, everyone now can do personalized fabrication very easily. In case we have a mechanism design, we can fabricate it very easily by sending it to a desktop 3D printer. However, designing a personalized mechanism to realize user-specified motion is still a challenging task that beyond the capacity of general users. To bridge this gap, there is an interest and need to study computational methods for designing personalized mechanisms in the computer graphics community. For example, designing mechanical toys that can display user-specified motions. We call this research topic computational design of mechanisms. In computational design of mechanisms, a mechanism is automatically generated and optimized to realize user-specified motion transfer task. In particular, users can specify the input motion, the output motion, and the effect shape, and so on. These computational methods model the geometry and the kinematics of a set of template kinematic pairs that can transfer basic motions. The computational methods automatically select and connect the template kinematic pairs to form a working mechanism that can transfer the input motion to the output motion. For computational design of mechanism, the first step is to model a library of kinematic pairs as the building blocks of mechanisms. First, we choose kinematic pairs and parameterize their geometry. Next, we model kinematics for each kinematic pair by computing the motion transfer function. Lastly, we define rules about which kinematic pairs can be connected and how they should be connected. Look at this example. There are two kinematic pairs. By merging the yellow part on the left and the blue part on the right, we connect the two kinematic pairs into a more complex mechanism. The second step is conceptual design, aiming to determine topology of the mechanism, which should satisfy at least two requirements. First, the mechanism is able to realize the user-specified motion transfer task. Second, the mechanism can be constructed from the kinematic pairs in the library. The method to compute a motion transfer graph that represents the motion, the mechanism topology. Look at this example. The input motion is the two rotational motions from the motor in black, while the output motion are the motions of the four end effectors, namely head, tail, and two wings of the bunny. Based on the kinematic pair library, we can find missing nodes in the motion transfer graph. Each edge in the graph corresponds to a kinematic pair in the library. By connecting these kinematic pairs following the graph, we can obtain an initial mechanism. However, although the initial mechanism can realize the out motion conceptually, it still cannot achieve it physically. For example, the initial mechanism is not completely inside the toy body, and collision exists. Moreover, the initial mechanism is bulky, which requires more energy to drive its motion. To address these issues, we need to perform geometry optimization on the initial mechanism. The objectives of the optimization can be maximize motion similarity or minimizing mechanism weight, size, and so on. The constraints include collision-free motion, joint motion range, fabrication constraints, and so on. And the search space is the geometry parameters of each component kinematic pair in the library. By this, the optimized mechanism is lightweight and compact, and able to perform the user-specified motion tasks without collision. To make the mechanism geometry ready for fabrication, there is some additional work to do. First, we need to place one or more actuators to drive the mechanism. Second, we need to construct a structure for supporting the whole mechanism. The support structure usually has complex geometry. In this case, we need to partition the support structure into parts for fabrication. So until now, we have introduced a general method for computational design of mechanisms. Now I will introduce some challenges in computational design of mechanisms, which also provide opportunities for future research. First, it is challenging to model and design kinematic pairs with novel geometry, such as 3D cam follower string on the top and 3D gears at the bottom. These kinematic pairs usually have stronger capacity to transfer complex motions, and the cost is that they have complicated geometry that has not been studied before. The deep dive speaker, Yingjie Cheng, will introduce more details about his research on modeling and designing 3D cam follower mechanisms. The second challenge is to model dynamics of mechanisms. In dynamic modeling, friction is always difficult to be precisely modeled and simulated. In case we consider tolerance in the mechanism, the dynamic modeling will be even harder. In traditional mechanisms, each mechanical part is modeled as a rigid body. However, flexible parts and joints have advantages under some user scenarios, for example, for manipulating fragile objects. Modeling mechanisms with flexible parts or joints is difficult because we need to simulate deformation behavior of these flexible materials. Many mechanisms only have one degree of freedom and can be driven by a single motor. However, mechanisms with multiple degrees of freedom is harder to model and design due to their high dimensional motion space. When designing mechanisms for robotic applications, there are two additional challenges. The first one is to control algorithm to sync motions of different mechanical parts for accomplishing a task. The second one is robotic prototyping, since besides 3D printed parts, we also need to assemble and install many electronic parts, such as controllers and sensors. Summary. In this motivational talk, I have introduced that a mechanism is a composition of kinematic pairs. Each kinematic pair enforces a constraint on the mechanism's motion, and the mechanism's kinematics can be computed from these motion constraints. Next, I introduce a general method for computational design of mechanisms with 4 steps. First, model a library of kinematic pairs, including their geometry, kinematics, and connection rule. Conceptual design to determine the mechanism's topology. Geometry optimization on the mechanism to satisfy various design objectives and constraints. And mechanism finishing to make the mechanism geometry ready for fabrication. Lastly, there are several challenges in computational design of mechanisms, which also provide opportunities for future research. With this, I conclude my talk and thank you for your attention.
Okay, thank you, Professor Song. And let's welcome next speaker, Yingjie Cheng. Yingjie Cheng is a visiting student at the Computer Graphics Laboratory in SUTD, supervised by Professor Peng Song. He's currently a PhD candidate in the School of Mathematics, University of Science and Technology of China, USTC. He received his bachelor degree in math from School of Mathematics, USTC in 2018. His research interests are computational fabrication and computer graphics. Let's welcome Yingjie Cheng to present the deep dive part of this talk.
Thanks, Runing, for the introduction. Hi, everyone. I'm Yingjie Cheng. Professor Song just gives a nice talk overview about the computational design of mechanisms. In this talk, I'm going to share our recent research on path generation mechanism, modeling, and optimization. Here, we show an example about path generation mechanism, which is a 4-bar linkage. When the left bar is driven by a single motor, the endpoint on the right bar will generate a path, say the arc in purple. Path generation mechanism typically required a single motor to generate. This brings several advantages, like low cost, energy effective, and easy to control. In construct, robotic arms require multiple motors to drive, require additional control algorithms. Due to these advantages, path generation mechanisms are used in widely variety of applications, including drawing machine, mechanical automata, and robotic locomotion. Designing a mechanical to generate a given path is called the path generation problem. Path generation problem can be classified as 2D or 3D, depending on whether the precise path is planar or spatial. As for 2D curves, here are many related research. Here are two results using planar linkage to approximate the path of the leg motion. In the left, the red curve is the target curve and the white curve is actually output. The input and the output have a previously distance, since the linkage only have finite geometry parameters, can only approximate target curve in a finite dimension space. In addition, the researcher can design a mechanism to interpolate some planar points. Here, the end effector of this 4-bar linkage goes through 3 points, points 1 to 3. Okay. However, if there are more target points or a continuous path, this mechanism does not work, cannot pass all of them. So they cannot exactly follow a continuous path. For exact generating a 2D path, the researcher combines a planar linkage with a 2D cams. The idea is that the cam can continuously change the length of the link while moving. Since the shape of the cam lies in an infinity dimension space, the cam linkage have ability to exactly generate a 2D path. As for 3D curve, the researchers have used a similar method to design a special linkage to approximate a given path. This approach depends on the database method, which is created before the design. If there is not a closed case in the database, then the final optimal result would be bad. Therefore, they can only approximate some simple 3D curves, like an arc or a line. Similarly, special linkage can be used to interpolate some points. With the same reason, they cannot exactly generate a 3D path. Now, the researcher can approximately or exactly generate a 2D path and approximate some simple curve with spatial linkage. However, how about to exactly generate their 3D path, such as this star, which is lying on a spherical surface? To solve it, I'm going to introduce our recent work on exact 3D path generation. The paper title is Spatial Temporal Motion Control via Composite CamFollow Mechanism. This work has been published at SIGGRAPH Asia 2021. In this work, our goal is to design mechanisms for exact path generation. The user can specify a target path represented as a smooth, free-form closed 3D curve. Here is a star in spherical surface. The user can also specify timing requirement on the motion, represented as the set of key points on the target path, as well as time interval between each pair of key points on the timing slider. The distance between 2 points on timing slider is time interval. For example, the end effector moving starts from the red point, and a black point moves evenly on the time slider, while the black point reaches key points, and the end effector reaches the same color key point on the target path. Taking the user-specified path and timing as input, our goal is to design a mechanism whose output motion can exactly follow the path and the timing. We choose CamFollow mechanisms, abbreviated as CamMech, as building blocks to achieve our goal to exact path generation. Look at this commercial CamMech. The big sign part is 3D cam, is a cylindrical with groove on it, which can be driven by a motor. The follower is in orange. It is driven by the cam's rotation. And the support structure is in gray. It is fixed in space to hold all of other parts. As aforementioned, the conventional CamMech can only output motion paths such as a linear path shown here, just some simple paths. The reason of the simple motion path is that the 3D cam can only push the follower along a specified direction, since the cam-follower joint is modeled as a cylindrical move-in groove joint. Simple force leads to simple motion. Inspired by this observation, we propose a new 3D CamFollow mechanism that can generate a free-form, closed, smooth path. In this example, our CamMech mechanism can generate a gingerbread man. The major difference from the commercial ones is that we model the CamFollow joint as a ball move-in groove joint. The groove is actually the envelope volume of the CamFollow joint ball while moving. By this, our cam can push the follower along a variety of directions of transformed complex motion. One cost of this modification is that our 3D cam is not a height field anymore, and should be fabricated by 3D printing instead of CNC milling. We also model different types of follower support joint to support different types of output motion. This is because follower support joint determines the types of follower's output motion. In this example, the follower support joint is a modified ball joint. Hence, the follower can output 2 degrees of freedom rotational motion. By changing the follower support joint, we propose 6 classes of CamMechs that can output different types of motion. The first class can output 2 degrees of freedom translation by using a sliding joint. The generated path can be any freeform curves on a planar surface. The second class can output 1 degree of freedom oscillation and 1 degree of freedom translation by using a cylindrical joint. The generated path can be any freeform curve on a cylindrical surface. The third class can output 2 degrees of freedom rotation by using a modified ball joint. The generated path can be any freeform curve on a cylindrical surface. Our CamMech also supports output 1 degree of freedom motion, including 1 degree of freedom translation, 1 degree of freedom oscillation, and 1 degree of freedom rotation. The output path is a 3D line, an arc, or a circle. For each class of the CamMech, we parameterize the geometry of each part, including 3D cam, the sign part. The follow is in orange. Support are in gray. Cam follow joint, a ball move in groove joint, follow support joint with 6 different types, and cam follow joint, cylindrical joints. We also model kinematics of the CamMech by computing the motion transfer function according to the CamMech geometry. The motion transfer function maps the input motion from the 3D cam tau C to the output motion of the follower TF. This motion transfer function can be analytically computed based on the cam follower's constraint condition. This video shows the result motion of the kinematics modeling. The first constraint about the kinematics is that follower ball center is always on the pitch curve, where the PP is follower ball center, and the CS is the pitch curve, which is the central line of the cam groove, determining the shape of the cam. And the TC is cam's rotation matrix. So we get the formulation like this: PPT equals to TCT times CS. And the second constraint is the follower's geometry, which has different formulations for different types of the follower support joint. Take this CamMech 2R as an example. It can output motion on a spherical surface, where PP is follower ball center, and PS is follower support center. Distance between these 2 points, PP and PS, is constant since the follower is a rigid body while moving. We get the formulation like this one. This is the geometry constraint. With these 2 constraints, we can compute the position of the follower ball center and get the motion of the follower. See the video like this one. For dynamic modeling, our goal is to compute the required torque for driving cam, giving the follower's workload. While the geometry is fixed, the torque is related to 4 factors. First is cam's angular acceleration. Second one, follower's acceleration. Third one, follower's angular acceleration, and the workload, which is given. The first 3 of which has been calculated in kinematics modeling. And so we can solve it by Newton's second law. Assumption here, the friction is ignored since our dynamic modeling is to efficiently quantify the different designs for geometry optimization rather than precise physical simulation. And in actually fabrication, we add some lubricating oil to reduce the friction. The details about the dynamic modeling is by a 2-step method. Step 1, we model the follower's dynamic using the Newton's second law to solve the required support force N and the force point Pn. Then we model the 3D cam's dynamic to solve the required torque tau C to drive the cam. Here is the result, for example, about required torque in a rotation period. In all, our first contribution is modeling a single CamMech. We parameterized the geometry of this CamMech from the analytical equations to model their kinematics and the dynamics. and a single CamMech can only output a single path. Our second contribution is proposing a method to compose multiple CamMechs to form a working mechanism that can output multiple paths. Our idea is to model the composing processing following a tree structure. The resulting CamMech is called a Composite CamMech. This Composite CamMech can output 3 paths: a dot, a circle, and a line. There are 2 different ways to connect a pair of CamMechs. The first one is called multiple connection, which merges the 2 3D cams driven by the same motor. By this, the resulting mechanism can support multiple output motions. We use the sign circle for the 3D cam and the yellow circle for the followers. The arrows are the motion transfer function. So in multiple connection, Ci, Cj are merged into a parent node Pk in the right, and connecting with 2 children's nodes, Fi and Fj. The second one is chain connection. In the left, Ci drives Fi and Cj drives Fj. Now merge the follower of Mi with the 3D cam of Mj. So Fi and Cj are merged into Pk. In result, Ci drives Pk and Pk drives Fj. By doing this, the result mechanism can adjust the pose of the output motion relative to the input motion. In chain connection, the first CamMech must be output rotation, since its output is next CamMech's input. With these 2 constraints, with these 2 connections, we can compose multiple CamMech following a tree structure. In this tree, the root node is a motor, and the middle node must be Cam1R, since it can output a rotation. And each leaf node is an anti-factor. And in this tree, each edge is a chain connection, and the sibling relationship is multiple connection. Here is the result of complete CamMech following this tree structure. To compute the multiple output motions, we need to model the kinematics of the composite CamMech. We model the kinematics also following this tree structure. First, we replace each node from the part to its associated motion to get the dual tree. The dual tree of the connection is the motion transfer function tree, motion transfer tree. And model kinematics of composite CamMech is to compute the motion of each leaf node in the motion transfer tree. Here is the F4, F5, and F6 node. Since each CamMech motion has been computed independently, to get the motion of a leaf node, we can compose the involved motion transfer function from the root to the leaf node. Here is an example that shows how to compute F4's motion from the single motor D1. And for dynamics, the goal of dynamic is to compute the motor required torque to drive the whole composite CamMech under workloads. We can use a similar method by calculating from the tree structure. The required torque can be computed by accumulating from the leaves all the way to the root. Taking the composite CamMech modeling and approach as fundamental. Now we are ready to solve the composite CamMech design problem. A simple version of this problem is to design a single CamMech, exactly generate a single path. Our input is a smooth, closed target curve with timing constraints. And here is the curve QU with 3 key points P1, P0, and P4 on it. And the timing constraints We add 2 time intervals here. And our output is a single CamMech that can exactly realize the given motion. The objective function for single CamMech has 2 energy terms. The first one requires a small torque to drive the mechanism. Is for saving energy. And the second term is the length of the pitch curve. Requires a lightweight mechanism, which can save the fabricating cost. The search space has several parts. The first one is a distance L from the driving cam axis to follow joint central P aspect. And the second one is an angle theta, which represents the pose of the target curve relative to the cam axis. And the pitch curve CS, which is the central line of the cam groove, determines the shape of the cam. We have some constraints for the optimization. The first one, the motion trajectory. Output motion must exactly following the given. 2, the motion timing. And the effect must pass some point at specified times. 3, smooth cam groove. The radius of curvature of pitch curve is bigger than the radius of the follow ball. 4, motion type. For curves on a spherical surface, we must choose to use CamMech 2R since it can output the 2 degree of freedom rotational motion. And for 5, cam follower contact. The cam's velocity should be larger than the followers at the cam follower joint. Then the cam can always push the follower. We use a gradient-based method, MMA, to solve this problem, and we got my optimal result. This cam 2R can move exactly following a drop on a spherical surface. Now, let's move to a general problem of composite CamMech design. Our input are several target curves and time control for each curve, where Q1 and Q2 are planar arc, and Q3 is on a spherical surface. The time interval is 0.8 and 0.2. Our output is a composite CamMech that can realize the given motion. We can see the scorpion is already, it moves slowly, and while attacking, the action is so quick. We formulate the design as an optimization problem. Our object function has 3 energy terms. The first 2 are same with the single CamMech design. We want less torque and lightweight. The last term is requires a small motion envelope of the mechanism. Our search space includes geometry parameters of each CamMech, which has been mentioned in single CamMech design, and the layout parameters among all of the CamMechs. Our optimization has several constraints. Besides of the first 5 constraints for each CamMech, we need to avoid collision among composite CamMech. To design a composite CamMech, firstly, we determine the topology of this CamMech. The motto M1 is the root node. We choose suitable CamMech as leaf node according to the motion curves. For example, M4 is Cam2R since it can output a 2 degree of freedom rotational motion, and M1 and M2 and M3 are Cam1R since Q1 and Q2 are planar curves. So M1 and M2 and M3 only output 1 degree of freedom rotation. Then we add the intermediate node according to the angle alpha k. If alpha k is too large, we should add a Cam1R. You can see in here, alpha 3 is larger than 45 degrees. So we add a Cam1R M5 to chain connect M1 and M4. Last, we compose the CamMech according to this tree structure. After determining the topology, we iterated 2 steps for solving geometry. First, we fixed the layout parameters, optimize each CamMech with the gradient-based method, since all geometry parameters of each CamMech are differential. Then we fixed the CamMech and optimized the layout parameters with using a randomized algorithm. And iterate above 2 steps, we get the final result. Here showing this video. The scorpion is attacking. Now let me show some evaluations. We use the CamMech 2R to draw a leaf here. It can achieve complex curves. However, from left to the right, you can see the more details the leaf has, the bigger the cam is. To evaluate time control, we draw the same star with differential timing constraints. Say the 3 timing sliders above the mechanism are different. All of them can achieve the trajectory and reach the given points at specified time. Last, they can reach the end at the same time, but the motion is different. It's an evaluation about kinematics. We use CamMech 2R to draw a T-Rex curve on a spherical surface. And we fabricated it with 3D printing, FDM 3D printing. We use image-based object tracking to track the curve and show the driving curve. And last, we project the target curve to the image. The hot-stop distance between 2 curves is 2.2%, which could be caused by the fabricating assembly or object tracking error. We compare our CamMech with the previous work. The left one is the result generated by linkages and gears to approximate the target curve. The target curve and the output curve have a large distance, while our CamMech can exactly following the target curve. The cost is that our CamMech is bulky and can only be fabricated by 3D printing because of the complex geometry. Here are some results shown here. This is a drawing machine. In the left, we can use Cam2T to draw a car on a planer. And in right, we can use Cam2R to draw a flower, to draw flowers in a bowl. Here is a mechanical toys about boxing, which is achieved by 3 cams. More results. We design a 6-leg walking robot driven by a single motor. It can achieve the given gates to realize user-specified trajectory temporal motion. We fabricate 3D printed it. The robot can walk stable and smoothly on the ground. Summary of this talk. We present a new composite cam follower mechanism for exact 3D path generation on a planar, cylindrical, or spherical surface. There are 2 technical components. 1. Modeling geometry, kinematics, and dynamics of CamMech. 2. Composing multiple CamMech to form a working mechanism. 3. Designing and optimizing a composite CamMech to realize user-specified motion. Our 3D cam follower mechanism is for exact 3D path generation. However, this mechanism actually has limitations, one of which is can only generate smooth free-form paths on a planar, cylindrical, or spherical surface. It's not actually 3D curves. for a curve cannot be embedded into a two-dimension manifold, like shown in the right. It's complex curve. We are considering it cannot to following it. We are considering to combine CamMech with special linkages and gears to extend the capability. And our dynamic modeling does not consider friction, which may need a difference between the simulation and real-world fabrication. We may consider friction, even the tolerance in the future work. And for some applications like pick and place, the orientation of the object needs to be controlled during the motion. That is rigid body guidance. We may consider it in the future work. And that's all for my talk. Thank you for your attention.
Thanks, Yingjie, for his deep dive part of this talk. And now I got a few questions from audience. First is that possible to optimize path of multiple endpoints of one mechanism? And maybe Professor Song or Yingjie, anyone you can.
I think Yingjie, maybe you can reply to this question.
Okay, thank you for this question.
I put this question in.
Okay, I see.
Yeah.
At now, our mechanism can only achieve a closed path if a path has multiple endpoints, which first it should be finished in one line drawing. If we need multiple paths, if they have multiple paths and discontinuous or disconnect curves, we cannot achieve it. And for example, if they have have multiple endpoints, but we can finish it in one line drawing and we can achieve it.
Okay. And the other question is, can this kind of mechanism you propose in your paper can achieve any kind of curve, or in other words, any constraints or limitations of the target curves?
Okay, I will take the question.
Okay.
And the first is that our, as I mentioned, our output motion must be smooth, closed curve. And besides of this, this mechanism can only output the curves lies on like a planar, cylindrical, or spherical surface, cannot be really actually 3D curves. And due to the limitation of the joint angle, since we have the cam-follow spot cannot rotate maybe 360 degrees, they can only rotate in a cone of the spherical surface. So the space is limited into this cone. If the curves is giving is too large and out of this space, we cannot reach it.
And actually, I mean, I think this is a very good question. So, whether there exists a mechanism that can realize arbitrary curve. Yeah. So, I think this is a very fundamental problem, and actually, we are trying to address this problem, trying to, for example, combine the 3D CamFollow mechanism with linkages. So, yeah. So we are working towards this challenging problem.
Okay. I think this is the end of this seminar. Once again, thanks to speakers' inspiring talk and audience for participating this seminar. Okay, bye-bye.
Okay, thank you. Okay, bye-bye.
Thank you, bye.